Well, today we get to start a new chapter on trigonometric identities. I do like the way the book has divided up these sections. I mean, it's sort of a classical way of dividing them up, but they did it very well. They do a nice job with all the basic right triangle trigonometry and unit circle trigonometry in the first chapter, and then they do the graphs in the next chapter. Identities is a real important topic by itself, too. What are we doing with these identities? It turns out in the sciences you often get expressions that are messy expressions, but they simplify a lot because of identities. And so one of the important things of these trigonometric identities is their use in simplifying complicated expressions in trigonometry. Another one is in deriving new identities. That is verifying equations. And solving trig equations. So those three things, particularly the first two, we'll spend a lot of time on. And this first section is actually entirely review identities. And so there's no new material here. It's a matter of just taking the things you already had and trying to apply them to simplify expressions and verify equations. Just those two things at this part. And then in the next section, when they get more identities, they'll start solving trig equations. For instance, you can take trig functions of new angles that you couldn't before. That's included in this, actually. So recall, we had a whole bunch of identities. Some of the most important ones were these quotient identities. Let's write it this way. One, quotient identities. Where the tangent is the sine over the cosine, and the cotangent is the cosine over the sine. Those you use all the time. We're going to need those explicitly today to solve a bunch of these trig equations and simplify trig expressions. Another important set was the reciprocal identities. Sometimes when you pull this all together, it all makes more sense. It's kind of like you're building a model. All little parts just, it's hard to keep track of everything you did until you put the model together and you say, oh, it's a dinosaur. So this really helps pull everything together too. So reciprocal identities were, and there's 6 of them. We could say that the cotangent is 1 over the tangent. The secant is 1 over the cosine, and the cosecant is 1 over the sine. And then every reciprocal identity has a reciprocal. If the cotangent is 1 over the tangent, is this reciprocal? Then the tangent is the reciprocal of the cotangent. Right? Similarly, the cosine is the reciprocal of the secant. And the sine, the reciprocal of the cosecant. Okay. Now, these are called identities for what reason? Identity is a theorem that's true whenever everything is defined, right? So there are some places where cotangent isn't defined, and where that's the case, this doesn't hold. The tangent might be defined at certain places where cotangent isn't. And so you bear that in mind, that this only holds when both sides are defined. Those are the reciprocal identities then. Of great importance also was the Pythagorean identities.
Professor. Thank you.
First one is sine squared plus cosine squared equals 1. And you start to get a lot of these and wonder, how am I ever going to memorize all these things? Anybody got any ideas? How did you memorize these things so far? Some of them you kind of memorize in pairs, right? I just got this off the screen for the people online, but if you have the first three reciprocal identities, cosine is, or secant is 1 over the cosine, cosecant is 1 over the sine, and cotangent is 1 over the tangent. You instantly know the other 3, so you really sort of have to only memorize 3 of those. That's why I tried to present them that way. On the quotient identities, if tangent is sine over cosine, you know cotangent is cosine over sine, being the reciprocal of tangent. So it's sort of they kind of can be derived from each other, right? And similarly on this one, if sine squared plus cosine squared equals 1, what are the other two Pythagorean identities? These are the two that don't much and are hard to remember. How can I figure out the other two from this one? Anybody remember? The reason I'm doing this is trying to develop your long-term memory. Sometimes if you memorize these things, they go away after a class. I don't need them anymore, but if you remember how you got one from the other, you can kind of figure them out when you're doing with your kids someday, or you have to do it at work or whatever. What are the other two Pythagorean identities? Remember? If I divide this through by cosine squared, then I've got sine squared over cosine squared is what? Tangent squared, right? If I divide this by cosine squared, I get sine squared over cosine squared from the quotient identity as tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared by the reciprocal identity is secant squared, right? So if you just divide this through by cosine squared, you get this one. That's how I could remember this one when I first learned this stuff. And it was hard to remember this one. But that's why the book puts this one this way and the next one this way. 1 plus cotangent squared equals cosecant squared. Why would they put the 1 here on this one and the 1 over here on this one? Because how they got this one, they divided the equation through by sine squared. Sine squared over sine squared is 1. Cosine squared over cosine squared is, well, cosine over sine is sine, so that squared is cotangent squared. And 1 divided by sine squared is cosecant squared by the reciprocal, right? So see how these identities kind of, you can derive each other's. This is one of the things we're going to be about. We're going to use these now shortly to derive even more. And we'll see that these are very useful, and the ones we come up with are very useful also. I can't tell you how many times I took a lot of physics where you get this complicated expression, say, I wonder what that graph looks like. And then you'd use a trig identity, and it would just turn out to be a simple sine wave. But you had to use the identities to be able to deduce that. So that's one of the big important things here, being able to simplify these expressions using these identities and recognize, oh, it's just a simple sinusoidal wave or something. All right, there's the Pythagorean identities. Then how about the cofunction identities? So I'm trying to show you a little bit how to derive these so they'll stick in long-term memory later. What were the cofunction identities? Remember those? I'll show you the easy way to remember these. This is not the most general proof. The most general proof comes on the unit circle, but I want to prove that you can remember how to do this again. How can I prove the cofunction identities? Do you remember what they were? The cosine of x minus, pi over 2 minus, well, let's start with this one. Cosine x equals sine of pi over 2 minus x. Where did I get that from? Or 90 degrees minus x if you're doing degrees. How did I get that? Remember the proof of this one? We did it actually. But if you try this a few times in your head, then these things stick a lot better. Use the right triangle. This doesn't prove it for arbitrary angles, but it does hold for arbitrary angles, and this will help me remember it. If I put a right triangle with theta in one corner, not theta, x, I used x. Now, here's the opposite side. Maybe I'll call this A, and here's the adjacent side, B. And here's this one, C, right? The hypotenuse. The cosine of x is the adjacent over the hypotenuse, right? B over C. This is B over C. Adjacent over hypotenuse. Now this one here is pi over 2 minus x. Remember that? These two always add up to a right angle, right? So that the three of them add up to 180. These two have to add up to 90 degrees or pi over 2. If they add up to pi over 2, then this one must be pi over 2 minus the other one. So now what's the sine of this angle? It's its opposite side over the hypotenuse, the same thing, B over C. So the sine of this angle, its opposite to hypotenuse, is the same as the cosine of this angle, it's adjacent to its hypotenuse. That's how you prove this one. You just put a B over C in here. Cosine x is adjacent over hypotenuse, is to this angle, opposite over hypotenuse, is sine. And so you remember that triangle, and then you can always figure this out. The cosine of one angle on a triangle is sine of pi over 2 minus the sine of the complementary angle over the other corner. All right. And then why is it called the cofunction identities? Because cosine is the cofunction of the sine, right? And then it works for all the cofunctions. The cotangent of x is the tangent of pi over 2 minus x. You can do it in exactly the same kind of proof. The cotangent of this is adjacent over opposite, is to this angle opposite over adjacent. Cotangent. And so it's the same kind of proof, right? Cotangent is adjacent over opposite, B over A, but B over A is opposite over adjacent. So this one is its tangent. And similarly, the cosecant of x is the secant of pi over 2 minus x. And there's actually three more of these, because if they're cofunctions, they do this to each other. You don't have to remember cosine goes on this side, sine goes on this side. It goes both the directions. It's also true that the sine of x, sine of x is cosine of pi over 2 minus x by a completely analogous proof. Right? This to this for x is this to this for pi over 2 minus x. And so they're cofunctions of each other. The sine of x is also the cosine of the complementary angle. Similarly, the tangent of x is the cotangent of pi over 2 minus x. And the secant of x is the cosecant of pi over 2 minus x. So they go in cofunction pairs, sine with cosine, tangent with cotangent, secant with cosecant. Anybody remember any more identities? I have another group here. What else have we got? We also got the even odd identity, right? Every trig function is either even or odd, meaning it has that property of even functions that f of minus x is f of plus x, or the odd property that the minus comes out, f of minus x is minus f of x. So here's the first one. The sine of minus x is minus the sine of x. The minus comes out, it's an odd function, right? Cosine of minus x, though, the minus goes away. It says cosine of plus x. That's a statement that cosine is an even function. If you remember from your algebra class, this is precisely the definition of odd and even. In general, f of minus x is minus f of x, the minus comes out, is the definition that the function is odd. And this is the definition of the function f of x is even if you just replace cosine with f. So this just says these are odd and even functions respectively. Tangent of minus x. If I can't remember this one, how can I figure it out? As I said, I'm going through sort of some ways I can remember these things, so I don't have to just rote memorize them. I can kind of figure them out. Is tangent even or odd? Anybody remember? Yeah, it's odd. How do you know? How can you show it's odd really easily? Here's an easy way. This one will help you for other classes if you take higher math classes too, because we use this for other functions. I'm going to do the proof here, then I'll erase it just to put the identity. Tangent of minus x, tangent is sine over cosine of whatever angle you put in. So tangent of minus x is sine of minus x over cosine of minus x, just by definition, tangent. But now sine of minus x, the minus comes out, right? cosine of x, the minus goes away. Now you've got minus sine over cosine is minus the tangent. How about that? There's a proof that tangent is odd, given that you already know, if you just remember, sine is odd and cosine is even. So I'm telling you, you can memorize these two and figure these others out. And pretty soon they start to be memorable. You don't have to figure it out all the time. But if you figure it out a few times, that really, really helps to make it sink in. Sine is even, cosine is odd, tangent is easy to prove, right? How about cotangent of minus x? What happens? I get cosine of minus x over sine of minus x. It's just this one upside down. The minus comes out of the sine on the bottom, and the cosine on the top is just of x. I need to move this over. I'm not getting a help from the audience. I probably do. No, it was okay. Okay. And so this one becomes cosine of minus x over sine of minus x becomes cosine over minus sine. The minus comes out just like this one. Completely analogous proof. Just with the cosine on top and sine on the bottom. Goes with the minus comes out of cotangent. Cotangent is odd. How about secant of minus x? I'll do a proof on this one. Secant is 1 over cosine of whatever angle you have, right? Cosine is even, the minus goes away. Every one of these, either the minus comes out or the minus goes away. It's either odd or even. But 1 over cosine is secant. There's the proof that secant is an even function. Secant of minus x, the minus goes away, it's secant of x. Cosecant similarly is 1 over sine. So cosecant of minus x is 1 over sine of minus x. The minus comes out of the sine, and you get minus 1 over, oops, you get minus the cosecant of x, showing that cosecant is odd. So these four you prove using the quotient reciprocal identity. See how nice those are for proving these? Now what we're going to do shortly is use these, all these we have, to prove even more. If you got tired of logarithm properties, you probably get tired of these. But like I said, they're not too hard to figure out from each other. Now I want to erase these two here, the two proofs. And just put the final identities. But I think those proofs are real nice for being able to figure these out when you forget. Right? And what you find out is that two of these are even, cosine, and it's reciprocal. All the others are odd. You'd think, there's even and odd, maybe half of them are even, half of them are odd. Not so. This one's kind of hard to remember. And so I had a little trouble memorizing what I can do to memorize them, and you can memorize them however you want, is I could either figure them out like that, or just say cosine and its reciprocal or even, everything else is odd. But once you recognize that an even divided by an odd is an odd, and even divided by an even is an even, that kind of stuff from algebra, you can figure these out as quotients here. And that's what I did in the proofs. Any questions on all of those? Those are the ones that we want to make sure we know we're proving some things here now. All right. Now we can use these to simplify trigonometric expressions, many of them. And I'll say using these rules of thumb. What's a rule of thumb? Maybe that's an archaic expression. Sometimes I wonder when I'm using language that's kind of out of touch these days. I've heard recently that in the public school system, they no longer teach cursive. When I was a graduate student, my advisor wrote in this beautiful cursive, all the things that were on there, and it does a little faster to write, but students can't read it now. I have to print everything. Fortunately, I got in the habit when I first started teaching and printing anyway, but you just, sometimes I don't realize things have changed a little bit. What's a rule of thumb? It's just something that you go to in general, right? It's not an absolute, it's something that you generally do. So here they are. When you see a complicated trig expression, the first thing you do is try algebra, right? To see if you can simplify it. There are a couple different things, particularly with quotients. So I'll say e.g., meaning for example, get rid of quotients of quotients. That's something you did in algebra. If you had a quotient of a quotient, what did you do? You took top times bottom over middle times middle. So eliminate compound quotients. Sometimes you have to create them and then eliminate them. But I'll say eliminate compound quotients in quotients. Cancel common factors, right? There's a whole lot of algebra rules, but the idea is that these trig function expressions often come in quotients. And so you want to remember these rules and apply them. Eliminate compound quotients, cancel common factors. I'll say etc., but those are the two that are used quite often. And cancel minus signs as part of canceling common factors, for instance. And then another thing is you do in algebra is put things over a common denominator. So a lot of these are to deal with quotients, the things you do with quotients. You see like a trig function minus another trig function quotient, you try and maybe put both of them over a common denominator. So you can add them or subtract them. So all those basic rules of algebra come up a lot in trigonometry. Another one is to apply one of our many identities. All those things we just put up go into the mix. And what's going to happen section by section now is we're going to get new identities, section by section, and build. And it'll be a matter of using these same principles here, these same rules, just with more identities to throw at them. 3, if you're stuck, you can do this one. So if the first two don't do anything for you to make things simpler, like in this one, when I was in physics or some sort of chemistry or other class, sometimes I'd get an expression like this, 2 sine squared, maybe y equals 2 sine squared plus 2 cosine squared. And that'd be my answer after I solved the problem. How do I know how to graph this? What does the graph of that look like? Absolutely trivial, believe it or not. This is y equals factoring out of 2. I'm using factoring in algebra thing. Sine squared plus cosine squared. All right. But sine squared plus cosine squared is 1 by the Pythagorean identity. So this is y equals 2 times 1 or y equals 2. Its graph is a horizontal line, right? Y equals 2 like that. This graph is absolutely trivial. It's a straight horizontal line. And if you know their trig identities, you can see it immediately. But this is what happens in a lot of applications. You solve the problem, you get something like this. Then you apply the trig identity and say, oh, it's just a constant function, right? So that's what can happen when you apply an identity. You can make it a whole lot simpler to figure out its graph, to figure out its properties, its maximum and minimum, and so forth. That's part of the reason they asked you maximum and minimum in the last section for sines and cosines. So you can look, do this kind of thing. It's always important when you've got the stock market. Where was my stock at the highest point, right? A maximum, or where was the COVID virus most killing the most people? You can figure it out from the graph, right? Try now. You can try rewriting if you're stuck. If these don't help you, the whole expression, let's say everything, in terms of sine and cosine only. So these are rules of thumb. Sometimes you just immediately see a faster way to do it. But if you don't see an obvious way, this is my order for the way I often organize things, and it works on almost every problem in this section, maybe every problem. The book, I don't see putting an organized approach to this. They just give you the various things, and you are welcome to do these in various order. I'll just call this my rules of thumb for how I often can get to the solution of simplifying a trig expression. Now, finally, there's two more that apply later. These will be for now. And then for later, I'm going to put two more. One of them is to get only one angle. What does that mean? That means if you've got sine of 2 theta in the expression and sine of theta in the expression, you're not going to be able to tell much about it. But there are trig identities that allow you to write sine 2 theta in terms of trig functions of just theta. All right? So I'll say, for example, just theta, not 2 theta or 3 theta, etc. in an expression. That really helps to simplify things if you get just one angle. For now, we're only going to have one angle, but in the upcoming sections, we'll have to do that. That's very important. And you can push this one first, actually, often. But I'll put it down here because we're not going to have that yet. And finally, the expressions may occur in an equation, right? This is the second part here of what I mentioned at the beginning. You want to solve equations, and you want to derive new identities. If you're given an equation, say an identity, you can work both sides towards the middle. You can simplify on both sides and try and work toward a middle common result. That's a very nice way to make proofs. Sometimes it's just too hard to start with your premises and go to your conclusion. Sometimes you can start from the conclusion and write equivalent statements to get back to your premises. So to verify an equation, sometimes it helps. You can work both ends, both sides of the equation, to a common middle to prove an equation. So I'm going to say these are the big things that we're going to do the whole chapter. We're going to do this over and over and over, just getting more and more trig identities. What I'm trying to do here is sort of, when you buy a new model, people don't build models, little model glue and that sort of stuff so much anymore, but it was always really nice when you had the picture of the model there to see what it's supposed to look like. Right? You knew a lot more what you're doing, putting together all those little airplane parts when you knew where it was going. Same thing here. This is where we're going, right? So if you know that, I think I'll make all the rest of it. All right. Now, at this point, you're probably screaming for examples. All this stuff is heady and difficult. Do a couple examples out of here. In fact, maybe I can do. They've broken these up into some of these rules of thumb by themselves. For this first section, it says algebraic. Suppose I said simplify a sine x times cosine x times secant x. Suppose I was trying to graph this. I'm an engineer and I've got this signal coming through my circuit. It looks like y equals that. What's the graph of that look like? This is the first one, so it's supposed to be easy. That's the first algebra one. Number 5. Yeah, cosine and secant are reciprocals, right? What you can do is go through here. First, you use algebra. There's no algebra. It's just a product that doesn't simplify. You apply an identity. Well, I don't really see an identity that looks like any part of that. So I try rewriting in terms of sine and cosine only. If you're stuck, what you do is you use the reciprocal identities and the quotient identities to rewrite everything but sine and cosine. I've got sine x, cosine x. Secant x is 1 over cosine x by the reciprocal identity. Ah, those two cancel, right? This is just sine x. It's just a single wave going through there. Very simple picture. Now I can draw it. How about this one? This is number 9. Suppose I have cotangent x plus tangent x all over secant of minus x. How about that? What does that one look like? I bet I can simplify that. But this is common to get this kind of output in your science class and then say, I wonder if I can make that easier. How can I reduce that? Kind of tricky. If I, it looks like algebra might apply because if I had another expression, maybe I could put them over a common denominator. If I had quotients of quotients, I'd get rid of the compound quotients, all that kind of stuff, but it doesn't seem to quite apply. So I'll go to the second step. How about the second step? How can I make something easier with an identity? Well, secant is an even function, right? So I can just take that nasty minus away. Cotangent plus tangent over secant. So get rid of, and this sort of applies to step 4 there, get one angle. I don't want an angle minus x and an angle plus x. I get one angle. I said that comes up in upcoming sections where you get 2x and 3x, but let's apply it here to minus x also. Since secant is even, it goes away. Now what do? I'll go to step 3 and say I'm stuck, right? I'll write cotangent using the quotient identity, cosine over sine. I'll write tangent using the quotient identity, sine over cosine. And I'll write secant using the reciprocal identity, 1 over cosine. Now what can I do? This one's kind of a hard one. And by the way, what you're seeing is me go through these rules of thumb in order. And this will work. And you'll find that I think every problem in here will work with these rules of thumb. Because they're not trying to put some exotic thing that's real difficult in here. They're trying to get you used to the usual things you do. However, what often happens is you see something, some way to do this easier. And if you see a way to do it faster, do it. Elegant proof is worth doing instead of taking a long proof, right? However, if you get every step correct and get the right answer, I don't care if it takes a long time, you still get 100%. So the object is to be able to simplify this correctly to the simplest form, regardless if it takes you a lot of steps, but do it your easiest way, right? So now what do I do here? Well, it's just getting messier and messier, but in algebra, if I have a sum of quotients, I put them over the denominator, right? So let's try that. Let's call this, multiply this one top and bottom by this denominator. Call it cosine times cosine is cosine squared over sine x cosine x. So I'll multiply this one top and bottom by cosine, multiply this one top and bottom by the other denominator, sine, and I get sine squared over sine x cosine x, right? And on the bottom, I still have 1 over cosine. Right? See anything nice that happens now? I put them over a common denominator so I can add them, right? In algebra, when you take 3/5 plus 8, 7/10, what do you do with that to simplify it? You put it over a common denominator, multiply this one top and bottom. You get a least common denominator, call that 6/10 plus 7/10. So you say, oh, let's go 6 plus 7 is 13/10, right? You add the numerators over the common denominator. We're going to do exactly the same thing with these trigonometric expressions. However, one thing that isn't pointed out here is I could have done this by multiplying this one top and bottom by 10. This denominator got 30/50ths. And multiply this one top and bottom by this denominator, I get 35/50ths. And this would have been perfectly acceptable too. 30 plus 35 is 65/50ths. And then I recognize by canceling common factors that this is actually 13/10. This is 13 times 5 and this is 13 times 10. Let's write it that way. And this is what's happening over here too. I can do things the hard way and get there, and I'll give you a whole 100% on the problem. But better to see there's a least common denominator and add it simpler. Here, the least common denominator is just sine times cosine, so there's nothing simpler to do. But I do want to point out that sometimes you don't have to multiply top and bottom by each other's denominators. You can get a least common denominator like we did here and save a step. And that's what will happen in your proofs too. A lot of times you can save some steps by being a little clever. Now here, the reason I added got a common denominator so I can add the numerators. Cosine squared plus sine squared all over that common denominator. And then the whole thing over 1 over cosine x. I like to put parentheses sometimes to make sure I know where my quotients are. Now what should I do? This would be step 1 here that we just did. I'm sorry, step 1 and 2 and 3. We skip step 1 here, we use step 2 here, and then we use step 3. And what you tend to do is you'll go through these, and then you'll go back to the top, and you can iterate. We'll go through the 5 steps, come back through the 5 steps, come back through the 5 steps until you get a good result. And that's what I'm doing here. It's an iterative process, we call it, something that you do over and over, an algorithm like a computer would do. Now what do I do at this point? If I go back to the top, I can get rid of compound quotients. But in fact, you don't have to follow exactly those rules of thumb. What's probably easier is to use a trig identity. What's an easy trig identity that makes this better? Yeah, sine squared plus cosine squared is 1, so cosine squared plus sine squared. Okay, so I'll rewrite this as 1 over sine x cosine x by a trig identity, all over 1 over cosine x. Now I'll go back to the top, step 1, and say algebra, you get rid of your compound quotients, right? A quotient of a quotient, you write top times bottom over middle times middle. Or you can write this one times the reciprocal of this one. That's the same thing. Right? So top times bottom is 1 times cosine x, right? Over middle times middle, sine x cosine x. Now you see the algebra coming in, right? Cosine on top cancels the cosine on the bottom. I'm thinking of the top as 1 times cosine, and it's 1 over sine x, which is another trig identity, cosecant x, right? So look at this complicated trig expression, cotangent plus tangent over minus secant, secant of minus x. All that is a complicated expression for cosecant, right? And that's what happens a lot in applications, as you'll find that these things simplify quite a lot. All right, so there's some algebraic problems. And we'll use these rules of thumb. Now what we want to do also is look at some equations. Let's say verify the identity. We're going to make our own designer identities here. That's what we're going to do. Sometimes in a science or engineering class or other classes, you'll get down to say, I wonder if that's true, and you have to verify that this equation actually holds. You're trying to make some mathematical model or something. And these can be quite complicated too. Suppose I want to verify this identity that cosine x minus cosine cubed x is actually equal to cosine x times sine squared x. How about that? How can I prove that? Verify is a kind word for proof. So I hate to say that, but these are proofs of this part. And they're actually very important. Like I say, these come up in lots of mathematical modeling. Any ideas? You try these same 3 steps, 4 steps if you like, and then you can work both sides towards the middle. And what I'll say is for equations, you can put these first 2 down here up top. we'll start it that way. Since it's an equation, I'll go to step 5 first, actually. And I like to do this. This is not the only way to prove these. You can, if you want, you can just start here and work and work and work to here. There's other ways to do proofs also, but the common way, say here's the proof. Cosine x minus cosine cubed x is what I have on the left. Equals, equals, equals. I need to get it to cosine x times sine squared x. What you'll see most books say is that commonly you start working from the side that's more complicated. You don't have to. That's another rule of thumb that isn't always true, but it's less commonly true. But maybe I'll start with this side because it looks kind of complicated. These aren't too much different complications, really. They're about the same. I might use algebra here, right? The first step is algebra. Once I've said this is an equation, I'll write both ends towards the middle. I'll factor a cosine x out of here thinking algebra. Cosine x times 1 minus cosine x times cosine squared x makes cosine cubed, right? So there's factoring for algebra. See what I've got now? Wait a minute. Sine squared is 1 minus cosine squared by the Pythagorean identity, right? That sine squared plus cosine squared equals 1. This is a real common trick when you see a square of a sine or a square of a trig function. Remember, one of the Pythagorean identities can be applied whenever you want. Because of this one, if I just subtract cosine squared from each side, I get the sine squared is 1 minus cosine squared. And I replace sine squared with that. So that will come up in a lot of these identities. Replace a square of a trig function with the Pythagorean identity equivalent. Now I say, they're the same, right? This equals this equals this. It's really only a two-step proof, or one step in the middle. Not too bad a one. That's why it's first on the proof list. And that's the trick. Use the same things. Algebra, especially with quotients. Identities, rewrite in terms of sine and cosine only. But now you work both ends towards the middle. All right. We'll try a little harder one. When you start, that was an A, maybe I should put A on here for that one. We'll call this one B then. Suppose I want to show that 1 over 1 minus cosine in x minus cosine x over 1 plus cosine x. Oops, I'm sorry, the wrong one. Oh, getting the wrong one. 1 plus sine squared x over cosine squared x equals 1 over cosine x plus sine squared x over cosine squared x. Suppose I want to prove that one. Look, I did it. This is a square here. I just wrote this out. This is not. I'm going to delete that one. What's the quotient one here? I wanted. Let's try one of the other ones here. I don't like that one anymore. This one. Suppose I want to show that 1 over 1 plus cosine. minus 1 over 1 minus cosine of minus x is equal to minus 2 cotangent x cosecant x. Let's try and verify this identity. There we go. Well, first thing to do is try and get one angle. So cosine of minus x, I can rewrite as cosine x, right? This cosine is even. Cosine of minus x is cosine x. And I'll say what I want to prove, then let's write that as 1 over 1 plus cosine x minus 1 over 1 minus cosine of minus x equals 2 cotangent x cosecant x. I want to show that that's true. So first thing I'll do is replace cosine minus x with cosine plus x to get one angle. That was step 4. Cosine. So just replace minus x with x by the even identity. Now I try and get these two equal. And here's the algebra trick. When you see two things that are supposed to be equal, what you want to do is write them both as, if one of them's a quotient, you want to write them both as quotients. You won't make them look the same until they are the same. Unless you can get rid of the quotients here, you try and write this one as a quotient. So how can I do that? Well, I could do that in step 3 at the same time. I could get rid of this and write it all in terms of sines and cosines, and maybe that would make it easier. So I could write this as twice cosine over sine, using the quotient identity, times 1 over sine, using the reciprocal identity. So there we go. We're working up this way here, and over this way here. We're working both ends towards the middle. Now I say, how can I get those the same? I need to have the same denominator. You can sort of see this with experience, I'll point out. One of the big things here is to just practice and practice. It's like doing a sport or something. You can get there at the beginning. If you dribble long enough, you can get across the court, but the object is to be able to do this quickly so you can go to the test, right? Recognize it when you see it and working on your, whatever, the FAA or whatever, general dynamics or something like that. One of the things you do in algebra, when you see a difference of quotients, what do you often do with the difference of quotients? If I have 3, 6 minus 4 9s, what do I do with that in algebra? Yeah, I get a common denominator. I'll get a least common denominator. Multiply this one top and bottom by 3 and get 9/18. This one top and bottom by 2 and get 8/18. 9 minus 8 is 1 over 18. So you simplify it. We'll do the same thing here when we have a difference of quotients. We'll get a least common denominator. In this case, we'll apply this one top and bottom by 1 minus cosine x. And get this. And we'll multiply this one top and bottom by 1 plus cosine x and get 1 plus cosine x over 1 plus cosine x, 1 minus cosine x. And now what can I do with this? I subtract them over the common denominator, right? 1 minus 1, they cancel. Minus cosine x and minus cosine x, I get minus 2 cosine x all over the common denominator. 1 plus cosine x, 1 minus cosine x. Well, this is getting tricky. And one of the troubles with this method I just told you, I'm sorry if you need to move, go behind that monitor here. When you want to get two sides equal, you have to get them over the same denominator, right? You won't be able to make them match until they have the same denominator. How did I get these denominators the same? Well, I could go backwards on this one again, and I could say, this is, oh, I got a 2, that's good, it looks like that one, but you're trying to make them look the same. This one, let's say, is going back this way, is 2 cosine x over sine squared x, right? Well, I'll work back this way again, trying to match this one. Well, it's almost right. Now, sine squared, however, I remember from the trigonometric, the Pythagorean identity is 1 minus cosine squared. So again, working back this way, I could write 2 cosine x. That looks almost like the top, it's just missing a minus. Over sine squared is 1 minus cosine squared by the Pythagorean identity. All right. See what I'm doing? I'm starting here. I'm writing it as a quotient, so I match the quotient here. And then I'm going back. Back here, I didn't leave enough room, and the board's not big enough. And writing this is sine squared, and saying sine squared is 1 minus cosine squared, trying to get to this denominator. And now I realize I've actually pretty much got it, right? Because this one, if I multiply out on the bottom, maybe I've been going this way, coming down this end and coming up this end. If I multiply this out by FOIL, 1 plus cosine times 1 minus cosine, what do I get? 1 plus cosine x times 1 minus cosine x. This comes up a lot, I'll warn you. 1 times, it would do FOIL. 1 times 1 is 1. 1 times minus cosine x is minus cosine x. Cosine x times 1 is plus cosine x. And cosine times minus cosine is minus cosine squared. These two cancel, and I get 1 minus cosine squared. Does this look kind of familiar? It looks in algebra like this. A plus b times a minus b is always what? By the same FOIL. A squared minus ab plus ab cancels, minus b squared. So that's what we did here. A plus b and a minus b is a squared minus b squared. You'll see this come up a lot. And when I multiply this 1 plus cosine x times 1 minus cosine x, I can't put another arrow here, but it comes down from the last line. I'll write this as minus 2 cosine x over 1 minus cosine squared x, because that's how the bottom foils. And now I see it, right? Oops, except for a minus sign. I'm off by a minus sign. Here I've got a minus 2 cosine x over 1 minus cosine squared. Here I've got plus 2 cosine x over 1 minus cosine squared. So except for a minus sign, I've verified this identity. I wonder if, oh, maybe I know what I did. I forgot my minus here. This is supposed to be minus at the end. Minus, minus, and minus, and now they match. And sometimes that happens is you just leave something off somewhere along the way and you have to go back and fix it. Now I've got it. There's the proof. The two sides actually are equal. Any questions on that one online? You can take your mic off for a second and ask if you have any. But this is the kind of difficult proof you sometimes have to do. And sometimes you see something easier, right? But this is the step-by-step rules of thumb method. All right. Well, that's what I want to do on that section. The other thing to do then is to go and practice these. It's really, like learning a sport. You see how to do it a little bit, and then you just have to go try it. But what I like to do at the beginning of next class is just see if there's any questions right at the beginning, and we can work those ones that are hard. I don't want you to beat yourselves to death over these. I want you to go try them on where you get stuck bringing your questions to class, and probably half the time that's the same one that everybody else is stuck on too. So expect that kind of thing. So that's section 7.1 is really just a review of the identities already had and those rules of thumb to apply them to simplifying expressions and verifying trig identities. Now the object of the rest of the chapter is to introduce more and more and more identities and to use those similarly with exactly the same rules of thumb. We're going to now introduce the sum and difference identities. Forget what this is. I think it's 6, is it? Remember I had 5 in there. Sum and difference identities. Add to the fray here these. These I'm going to omit the proof on. You can look in the book. I believe it's in there. It's interesting, but it's not insightful like the other ones we did. We did a lot of proofs today to show you how you can easily figure these things out when you get stuck. This one is not short. It's not too long that we can't do it or too hard to do, but it's just, it doesn't give you insight. You can't go back and say, well, I can't remember this one, I'll figure it out. It doesn't, it's not so easy. So I'll say you can use the unit circle to prove this one. You draw your angles in the unit circle and it's kind of complicated. And here's what you get, and this is what we need for these. You have these, you kind of have to memorize. Then the rest of the chapter, the good news is we do start to be able to derive the next identities from these. There'll be double angles identities, half angle identities. Those will be derived coming from these. So the sum and difference identities of these, with a hand waving proof. Did I tell you to hand waving proof this before? They're doing lots of science classes all the time. And whenever you don't really want to prove something, you wave your hands real fast and dance, and everybody believes it, right? That's a hand wave. But you'll see that in a lot of science classes. Here we'll do more proofs, but not this one. Sine of the sum of two angles. Write X and I can't remember if these X and Y are alpha and beta now. We'll use the same letters. These alpha and beta, yeah. The sine of alpha plus beta is the sine of alpha, the cosine of beta, plus cosine of alpha, sine of beta. Absolutely have to memorize all of these and all the other ones I put up earlier. You already told you to memorize those, but I'll put a star by these. These are new ones to memorize. And then I'll leave a little space here and I'll say the cosine of the sum of two angles, hence it's called a sum identity, is cosine cosine minus sine sine. So that's how we usually say that to memorize it. Sine of the sum is sine cosine plus cosine sine. Cosine of the sum is cosine cosine minus sine sine. Putting the angles in the same order, alpha beta and alpha beta. All right. Those two actually encompass also the difference identities. Because suppose I replace beta, this will be a proof. Once you have these two, actually once you have the first one, you can prove all of them. But suppose in this one I replace beta with minus beta. This will help you memorize the next one. If you memorize this one, you can figure out the next one. Suppose I replace beta with minus beta over here. What happens over here? I replace beta with minus beta here, and beta with minus beta here. And now this becomes over here sine of alpha minus beta. Right? If I replace beta with minus beta, equals sine alpha, cosine of minus beta, cosine's even, right? The minus goes away. So cosine of minus beta is going to be the same as cosine beta. And then plus cosine alpha, sine of minus beta. On sine, the minus comes out, and I get minus sine beta. So if you just replace beta with minus beta in this equation, you get this equation. Because the minus comes out here, the minus goes away here, and the minus stays here. And you get this identity, which is this difference identity. All right, sine of a difference of two angles. Is sine cosine minus cosine sine. You want to memorize this one, but if you forget it, you can figure it out from this one. I really like that about this. And similarly, how about the cosine of difference two angles? Suppose I replace beta with minus beta here. This holds for any angles alpha and beta, right? So if it holds for beta, it holds for minus beta. So this identity implies you can replace beta with minus that angle. And if you do, what do you get? Alpha plus minus beta is alpha minus beta. And then cosine of minus beta, cosine's even, the minus goes away. Right? Cosine alpha, cosine beta, minus goes away. Minus sine of minus beta, the minus comes out and cancels this minus, changes to a plus. Sine alpha, sine beta. See if you can memorize the third one, you can figure out the fourth one by replacing beta by minus beta in the third one. I'll erase these because what I want is for you to memorize all four of these. But I did want to point out that it's easy to prove this one by putting minus beta here. It's easy to prove this one by putting minus beta here, just in case you forget. There is the sum and difference identities for sine and cosine. We're also going to get some for tangent. But the last three functions besides sine and cosine and tangent are not as important. People tend to not memorize those. They aren't used as much. So we're almost done with sum and difference identities, but not quite. These can be used to simplify trig expressions, prove, verify identities, and one more thing, they can calculate now exactly trig functions of some new angles. So I want to use those to do that first, and then we'll go back to simplifying and proving. Not sure if I have time to do that today even, but we'll say, in addition to simplifying expressions, just as we've been doing, and verifying identities, we can now calculate trig functions exactly of new angles. What angles are they? They're any multiple, instead of 30 or 45 degrees, any multiple of 15 degrees. Some of your calculators can do this too. Some of them can't. You can get exact expressions now for any multiple of 15. I can do sine of 15 degrees or 75 degrees or 105 degrees. Those that I couldn't do exactly before, I can now do by hand exactly. What is 15 degrees in radians? Pi over 6 was 30 degrees, so 15 degrees is half of that. Pi over 12. Now we can do exactly any trig function of an angle that's a multiple of pi over 12 radians or 15 degrees. How about that? And here's the way you do it. This is the easiest one. I like to always do this one first. Suppose I take the sine of 15 degrees. What is that exactly? What you can do is say 15 degrees is actually 45 degrees minus 30 degrees, right? By subtraction. And now that's cosine of a difference, right? Cosine of alpha minus beta is cosine, cosine plus sine, sine. So if you think of this as alpha, and this is beta in the formula, it's cosine, cosine, plus sine, sine, putting the angle in order. Minus beta, it's cosine, cosine plus sine, sine by equation 4 there. But these are all special angles that we already know how to do from the special triangles, right? So I can remember these. There's a 45, 45, 90 triangle. And there's two ways we memorize this. We could either say it's 1, 1, and square root 2. Or the other way we did it was we put the one we put in the unit circle is square root 2 over 2, square root 2 over 2, 1. And you can use whichever one you like, it doesn't matter. What's the cosine of 45 degrees? Adjacent over hypotenuse, or you just put it in the unit circle and say it's square root 2 over 2. All right, so adjacent over hypotenuse is square root 2 over 2. Now the other one we had was 30 degrees. Suppose I gave you, I like to do it this way usually, with the 30-degree angle up here. This has been 1 square root 3 over 2, or 1/2 square root 3 over 2 and 1 is the one that fits in the unit circle. But if you like the one that's double this one, 1 square root 3 and 2, that one's just fine too. You can use either the unit circle version, if you're doing the unit circle, or you can use the one without quotients, 1 square root 3 and 2, whichever one. Cosine then of 30 degrees, here's the 30-degree angle, it's adjacent over the hypotenuse, is square root 3 over 2 over 1, or just square root 3 over 2. And then plus sine 45 degrees, well, that's opposite over hypotenuse, is square root 2 over 2, or you can just say it's the y-coordinate of the unit circle, doesn't matter. The reason I keep mentioning the unit circle here, even though I don't need it, I can just use the triangles, is what if you get an angle that's bigger than 90 degrees or that's negative? Then you need the unit circle. So on these ones where the angles are in the first quadrant, I recommend just using the triangles, it's easier. But when you get angles that are not in the first quadrant, then you have to go to the unit circle anyway. So I'm mentioning that as we go along. Sine 45 degrees is opposite over hypotenuse is square root 2 over 2. Oops, there we got it. And then times sine 30 degrees is opposite over hypotenuse is 1 over 2. 1/2 over 2. All right, so there it is. And now what happens is here that there's often some nasty quotients to deal with. I'm going to bring this back over here, so I'm right behind the monitor again. You notice these have a common denominator, right? When you multiply quotients, it's top times top over bottom times bottom. So this is square root 2, square root 3 is actually square root 6, right? Remember this property, square root A, square root B for A and B positive non-negative numbers is square root AB. So all right, square root 2 times square root 3 is square root 6. All over 2 times 2 is 4. And then plus square root 2 times 1 is square root 2. Over 2 times 2 is 4. This expression is exactly square root 6 plus square root 2. Got that botched it. I used the wrong identity. Cosine of, let's see. I did the wrong one. I did, you gotta say something. I did the wrong problem here. Cosine of 15 degrees. Cosine of 15 degrees is cosine of 45 minus 3. I don't know what I was thinking. Sorry about that. Cosine of 15 is cosine of 45 minus 30. I'm calculating cosine here, not sine. All right, and so I get square root 6 plus square root 2 all over 4. There's the exact expression for cosine of 15 degrees. Sorry about that. Any questions on that one? Let me do at least one more, and then we'll get back to these sum and difference identities next time. So I did a cosine one. This is the cosine of the difference of two angles. What if I've got some more difficult angle? I can do the same thing. It's just I can't use these special triangles. I need to use a circle. For instance, this time let's use the sine. Suppose I want the sine of 165 degrees. Can I do that exactly? How do I know? It can be done exactly if it's a multiple of 15 degrees at this point. And actually later we'll be able to do some other angles too, but for now we can do any multiple of 15 degrees. How do I know it's a multiple of 15? There's a couple ways. If you put it close to a special angle, remember like 180. Oh, this is 180 minus 15. All our special angles are multiples of 15 already. So if this is 15 from a special angle, then it's a multiple of 15 degrees. So this is 180 minus 15. And I say, oh, that's 165. So this is a multiple of 15. It'll work. The other way to think of it is 10 times 15 is 150, and this is only 15 from that. That must be 11 times 15. Obviously, this is multiple of 15 if it's 11 times 15. So either way, put it 15 degrees from a special angle or a multiple of 15 from a special angle. Or figure out a multiple of 15 that comes close and see if you get a difference. It's a multiple of 15. Sine of 165, the trick is to write this as a sum or difference of two special angles. That's what I did here. 15 degrees I wrote as a difference of special angles. Let's do that here. This one, write 165 since it's a multiple of 15. Multiple of 15 degrees implies write this angle as a sum or difference of special angles. It can always be done when it's a multiple of 15 degrees. How can I write 165 degrees of sum or difference of special angles? Special angles are multiples of 30 and 45.
You do 135 plus 30.
Yeah, I could do that. Okay, let's do that. Sine of 135 degrees, which is a special angle, plus 30 degrees. This time I'll use a sum formula, and for sine instead of a difference formula for cosine. Erase this one. I will say sine of the sum of two angles is sine cosine plus cosine sine, the very first identity you wrote, right? Just remember that sine cosine was cosine sine, and then you put the angles 135, 30, 135, 30 in order, right?
Professor,
Yeah.
Could you move the camera just a little?
Oh, I'm sorry, yeah.
Thank you.
All right, so sine of the sum of the two angles, sine, cosine plus cosine, sine. And now I need the unit circle because these 135 degrees doesn't fit the right triangle. So I'll go over here and I'll sketch 135 degrees, bigger than 90 and less than 180. In fact, if you figure it out, this angle left over in order to add up to 180 must be 45, right? 135 plus 45 is 180. So my reference angle is 45, I'll get a special triangle. And now the coordinates of the point, this side is square root 2 over 2, this side is square root 2 over 2, and 1 we memorized, 45, 45, 90. So the coordinates of the point are minus square root 2 over 2, I went left, plus square root 2 over 2 since I went up. That's the cosine and the sine of that angle we learned. So we can apply those to the 135 degree angles. Say sine of 135 is plus square root 2 over 2. And then we need the 30 degrees. We don't need a special unit circle for that. We can just use the special triangle. It's easier. So again, I'll put the 30 degree angle in here. And this is 1/2 square root 3 over 2 and 1. Or you use the angle, the triangle as double these. And let's see, the cosine of 30 degrees is adjacent over hypotenuse is square root 3 over 2. Now cosine of 135 degrees is the x-coordinate here, minus 1 over square root 2. Excuse me, minus square root 2 over 2. And sine of 30 degrees is opposite over hypotenuse is 1/2. There it is. Once again, I'll get a common denominator. Square root 2 times square root 3 is square root 6. 2 times 2 is 4. And then now plus a negative is minus square root 2 times 1 over 2 times 2 is 4. This time I get square root 6 minus square root 2 all over 4. There's the exact expression. These radicals, these square roots here, maybe you remember from algebra, the square root of every whole number is either a whole number or what's called an irrational number. A number that goes on forever without a repeating pattern. No matter how you try, it can't be written as a fraction. So these go on without a repeating pattern forever. Wherever you round your calculator result off doing this in the calculator, it will not be exact, right? Because you can't get an infinite number of digits in your calculator. So this is the exact expression. Any decimal you write on your test will be wrong. All right, so take a look at those. We're about out of time. Look at 7.1 on the supplement. Do all of the problems there. There's not very many. I may actually assign a few more next time. But at least try all of those. There's more than we did in class. And then 7.2, I think I'm going to have to wait. I didn't get far enough probably to ask anyway, but let's see if there's a couple I might get you going on. We could do 1A, B, and C. Let's do that. Because they're just like these. All right. Any questions on those next time? We'll pick up some more angles we can do and some more trig identities and simplification.